So in the previous class, we were looking at channel flow. We have started looking at exact solutions of the Navier-Stokes equation. We started looking at channel flow. So we have two flat plates, long flat plates. There is a uniform flow which is entering this. The gap region. And then we said that there will be a boundary layer that will form from both the walls, which will merge. And then there will be a fully developed region. So we want to do our analysis in the fully developed region. So in the fully developed region, we also assumed it is steady, fully developed. And I'm not going to write incompressible and Newtonian every time. So that is sort of given to us. Till there is a deviation from there, from those two, I will not explicitly note it down. So here, for this case, we had said this is the x direction, this is the y direction. We said in the fully developed region, the flow stops changing. So dou u dou x becomes 0. And anyway, along the z direction, plate is very long. So there is not too much action happening there. So starting from the continuity equation, we can see that because of the fully developed condition, dou u dou x is 0. The first, and this is the continuity equation. So this term is 0, which gives us that v is not a function of y, and we have already argued that v is not a function of any other thing. So that means v is a constant, and that constant will take the value of whatever it is taking at the wall, and at the wall v is 0. So that has to be 0 throughout. So that's how we deduce that v is equal to 0. Now, if you go to the y momentum equation, we only get dou p dou y is equal to 0. Other terms which are all derivatives of, or v is involved in all of them, and because v is equal to 0, all the other terms drop off, and we simply get dou p dou y is equal to 0, which means that pressure is, so this is coming from the continuity equation, or this is the continuity equation. This is the simplified form of the y momentum equation, that dou p dou y is equal to 0, which means that pressure is not a function of y. Okay, so then we are left with the x momentum equation. So we write down first the x momentum equation, the 2D form of this. So this is the final equation, and this is where the most important equation, this is where the action is happening. We say that this term is 0 because it's a steady situation. We have already seen that this term is equal to 0 because it is fully developed. Okay, v is equal to 0 from the solution of the continuity equation. We did not know that beforehand. And again, because of the fully developed condition, dou u dou x is 0, and therefore throughout, okay, it's not just for any one, it could happen at one point. So we are not talking about one point. This is a confusion which was raised by a student the previous class. So we are not talking about one point, we're talking about everywhere. Okay, so that means if I'm looking at everywhere, then the second derivative should go to 0, has to be 0. I mean, it just the function is 0 everywhere, so its derivative of that is clearly 0. So then we are left with only two terms, which are these two terms here. So I get the x momentum equation simplifies to that dou p dou x is equal to mu times dou to u dou y2. Okay, Now, if I look at this equation, before trying to solve this, let me just put a few comments. The first comment that we see is that the inertial term has dropped off altogether. Okay. So, I mean, if you recall the derivation of the Navier-Stokes equation, we said force mass times acceleration on one side and forces are on the other side, right? So, you can see that there is no acceleration in this case, okay, which is what fully developed means. The velocity is not changing, the flow is not accelerating, and because it is also not steady, okay, so acceleration is identically 0. So, you can see that the left hand side is identically 0, and therefore, what it means is that how will the balance be now? It has to be by all the forces. There is the forces are not 0, but the sum of the forces are 0, or the resultant of or vector sum of, let us say, vector sum of all the forces is 0. So, that is the situation that we are talking about here. And a consequence of that, if I look at this equation versus this equation, if I look at the point of view of a property, what has changed? That this solution is not going to depend on the density of the fluid. Okay. So, you can see that the density of the fluid is no longer appearing in this equation. So, that means any fluid with any density will still satisfy this. It is irrespective of the density. So, okay, so that's the conclusion that we get from here. Now we can again go back and examine what is pressure a function of, and this is of course the set that we have to always consider. P is not a function of T, steady we have already taken out, 2D we have taken out Z. So, you can see that P could have been a function of X and Y. But now we are going to use our result that P is not a function of Y. Okay. So, that means that pressure is only a function of X. So, we can change this partial derivative to total derivatives. And if I look at U, if I do the same thing, so again these two are easy to remove, and we already know from the fully developed condition that U is not a function of X. Okay, so that means that I am left with that U is only a function of Y. So again I change that to a total derivative. Now I have to solve this equation. How do I solve this equation? So this is also telling us that pressure is only a function of X. Okay, so this is some quantity, pressure is function of X, and therefore the derivative of pressure with respect to X is also some function of X. Okay. On the right hand side, we have velocity, which is a function of Y, and of course the derivative of that can be a function of Y. Okay, and what is the nature of X and Y? They are independent variables. So I can change X, okay, but I can hold Y constant because these two are independent variables. So I can hold X and change Y. So that means I can change this quantity, but I'm holding this constant. So that cannot, there is a contradiction here. Okay. And similarly, if I change Y, I'm changing this quantity, holding this constant. So then there is a contradiction here. So that means that only way that it can be satisfied is that they are neither left hand side is not a function of X, this is not a function of Y. So they are constants. Okay. So that's the only way that the equation can be satisfied. Okay. Any questions here? Because this is now the formulation. Now it's a matter of just solving this equation, and which is reasonably trivial, and we will have the solution. Okay. So before that, setting up the problem and how did we go about simplifying it has to be understood. Okay. So I'm assuming that people are okay with this. So there are two parts to this. One, we can say that pressure varies linearly. And it is clear that pressure is not going to increase, pressure can only decrease. Okay. So then dP dx is going to be negative. Okay. So that's one thing that we can say. So pressure varies linearly. So here we can even say decreases linearly. I can realize And the second part is I can now take this part and integrate this, which is of course trivial. So I get u is equal to k by mu times y square plus c1y plus c2, where c1 and c2 are the two integration constants that get generated upon integrating this equation. So what is the value of c1 and c2? That needs to be determined from the boundary conditions. So what are the boundary conditions here? So y is equal to 0. So let us write out the boundary conditions, which we had never done for this case before this. So at y is equal to 0, u is equal to 0. What else? Y is equal to h, u is equal to 0. Okay. What about Okay, so do here we can just change it to total anyways. Do u du dy is equal to 0 at y is equal to h by 2. So we are now having three conditions. I only need two. So what do we do? Yeah, so you will find that you can pick two and the third one will automatically get satisfied here, because this one is only coming from symmetry, and this symmetry is because these two are equal. At the two walls, velocity is equal, and because of which this condition is there. Okay, it's better sometimes to use this, and I mean one condition at the wall. And where are these two conditions coming from? These two conditions are coming from the no slip condition, that the flow cannot slip at the surface. So they are the no slip conditions, and as a consequence of that, at the center line, because we get the same situation on both the walls, at the center line, at the center of the distance, the gradient should become 0. Okay, so I mean, if you use this condition, what is the final solution that you would get? Let us just do that. Okay, by the way, any questions here? Any questions? Yes. Its density is absent. Basically, it does not depend on the fluid density. I mean, so you keep on changing the fluid density. So the solution is only depending on the viscosity. Yes. So if I take a fluid, for example, and I add certain things to change the density and keeping the viscosity same, okay, nothing would change. Okay. But on the other side, if I keep the density constant and change the viscosity, okay, so it is possible, by the way. This is what I'm saying is not theoretical. It is actually can be done by experiments. So then you can do change the viscosity. Then you will find that the solution will something will change in there. So essentially, you are saying that k by mu term is changing, and k is nothing but dp dx. Okay, so your pressure gradient would start changing now. Any other question? Okay, so let us just solve this completely. So I get that y is equal to 0, u. So the first condition, boundary condition 1, gives me that C1 is equal to 0. Okay, because y is equal to 0, everything is 0. Sorry, C2 other than C2. So C2 is equal to 0. And boundary condition 2 gives me that 0 is equal to k by mu times h square plus C1 times h, which implies that C1 is equal to minus k by mu times h. Okay, so I have everything now that we needed, and we can, yes. Sorry. Okay, h by 2. Yeah, you are right about that. So this is h by 4 here and h by 2 here. Thanks. Divided by 2 here. Thanks. No, this is being applied at h. No, why are we? This is we are applying the second condition. Sorry, which one? Boundary condition 1 or 2? Which one are you looking at? Oh, here you want to put a 2 here. This k, I mean 2 anyway can be absorbed in k also if you want. If you want to write it out explicitly, it's fine also. Okay, so this is correct now. So I get u is equal to k by 2 mu times y square minus kh upon 2 mu times y. So which gives me that k upon 2 mu times y if I take constant and h minus y. Right? I hope I have done it correctly. And of course, now if you want, you can check that. If you want to differentiate this at with respect to y, and then put y is equal to h by 2, you will get that this condition is automatically satisfied as we had claimed earlier. Okay, so we are not using the third condition. Let me just put a cross here that this is not required, and we are using only the first two boundary conditions. Yeah. Here is just integration. No? Here what was pointed out that if I integrate this, I will get ky first, and then I integrate it again, I get ky square by 2. Mu is coming from here. Sorry, 1 by 2 term. Where? Here only. This expression for u. So I just mentioned that you integrate it twice. So you get ky first, or k by mu times y first, and then again integrate it again, you will get k by mu y square by 2. Okay. So okay, one can use this expression to find out what is the value at y is equal to h by 2. So u at y is equal to h by 2. What is the value here? We can of course substitute it in this expression itself. So I get k by 2 mu times h by 2 times h by 2. Here y minus h. Yeah, you are right. So y minus h. So it becomes a minus sign here, right? So why is this minus sign coming in? This minus sign is coming in because k itself, as we had said, pressure decreases linearly. So actually it has a negative slope. Okay, so pressure is k is actually negative. Okay, so this velocity k is negative itself, is itself negative. Okay, so that is why this is going to become positive for you. So I get it in terms of minus k h square upon 8 mu. I hope this is correct now. I'm not doing it with notes or anything, so I may be making some mistakes here. You can point it out if there is any. Okay, so this is, you can call this as the centerline velocity UC. Okay, and then sometimes we can use this expression for UC to eliminate k. Okay, so k can be eliminated here from here as k becomes minus 8 mu UC divided by h square. okay, which I can now take in here in this expression here for u. This is the expression for u that we have, and we can substitute here, and I will get, so I get k u is equal to minus 8 mu uc upon h square times y minus h. Okay, so this is the expression that we are getting, and again, if we want to, sorry, okay, mu has to cancel out. So okay, so I think I have not done it correctly. So this is just we have substituted for k here, and then we have to put y by 2 mu, okay, times all this, okay. So I get minus 4, so this mu is cancelling out, and then maybe this minus sign we will absorb it in the other one. So I get 4 times uc upon h square times y times h minus y, because h is anyway greater than y. So this is a better form to write it out in as compared to whatever we had earlier, right? So this is just one way. I mean, there are several representations. We can keep on manipulating these equations. Maybe you can find out what is the volume flow rate or the mass flow rate. So mass flow rate you can find out. Okay, so it's like rho times h. Whatever is coming at the entrance, you can just say that that's what is coming everywhere. Okay, and in terms of whatever velocity profiles you have, you can estimate it from there as well, obtain it from there as well. You have to integrate u and obtain it, and you can show both of them the same, etc., etc. So there are quite a few things that you can do with it, all these expressions. Okay, is this clear? Any questions here? Okay, so that's a very good question. So the question that is being asked is that we have confined ourselves to the fully developed region. Why are we not looking at the developing region? And is it that the developing region is very small, it is insignificant, or is it because the velocities are just too widely changing and therefore we cannot say too much about it? So the answer is neither actually. We do analysis of the developing region also. Okay, in fact, at some point of time, I've been always debating whether to bring in the developing region, because that involves a little bit more maths. Here, this is taken as a first problem. In fact, if you sort of realize that this is the very first time we have solved Navier-Stokes exactly, and this is like a clean problem where one can get a very nice simple solution. One can justify each term why it is 0, and they're identically 0. They're not approximately equal to 0. So as I had mentioned when we started this topic, that there is something which is exact and something which is going to be approximate. So here it is, everything is exact. There is no approximations that we are making anywhere. So that is why it is easier to justify it, easier to, for first time when you're looking at it, to see and appreciate. Otherwise, people start arguing that this is this, that. I mean, of course, there is an answer. It's not that, and one can do a detailed analysis and figure it out in an approximate case. But here there are no approximations. So that is why this is done. Whereas when you go to the developing region, then you will have to make certain approximations. But now, we can still make, following up on whatever we have said, we can make a few comments on this. So if I were to look at the pressure distribution, so let us say this is the entrance, which is 0. This is the fully developed region. Okay, after this is my x direction. So after that, the flow has become developed, and this is, I'm plotting pressure here. So what we are saying is that if beyond this location, pressure is dropping linearly. So this is how the pressure is decreasing. Okay, now if I have to use this information and figure out what is going to happen in this region, so I don't know the exact expression, but let us say that I can say that, okay, if I were to extrapolate it on the left hand side, the pressure would, I mean, this is just a linear curve which I'm extrapolating on the other side. Now the question that I'm asking, will it be like this? Will it be like this? So this is my 1, 2, and 3. So 3 curves I have. 1 is linear, sorry, 1 is going up, bending up. 2 is linear, it's just extrapolated, and 3 is bending down. So which of these three applies and why? 1. Okay, so you can see that I mean, people are just able to guess the answer without any issues. And why is that? What is the justification? Flow is accelerating, therefore. So okay, so I think yeah, so therefore the pressure gradient. So let us understand, maybe okay, maybe spend one more minute on the equation that we have written, that dp dx is equal to mu times dtu dy. So how can we look at this equation? We already said that on the left hand side there is no acceleration, so all the forces have to balance. Okay, so what this equation is telling you, that this is how the forces are balancing. Now what is this force? The pressure force. So this is my pressure force and this is my viscous force, and in the fully developed region the only thing which is happening is that the pressure force has to balance the viscous force. Okay. Now in the developing region, what is going to happen? So and then we can even say that, okay, which one is driving force and which one is resisting force? I mean, unless and until there is a net force has to go to 0, acceleration will not go to 0. So both of them cannot be driving forces. It is clear. So one has to be a driving force, the other one has to be an opposing force, so that the net force is 0 and acceleration becomes 0. So you can it's very clear again that the pressure is a driving force, and this is viscous is of course always weird. I mean, if you don't know that, we can always look at this side and say viscous is always going to be dissipative, and therefore this has to be the driving force. Right? Now, when I come here, what is happening? Acceleration is not going to be 0. Okay, so I need some force to accelerate. Right? So I need a force to accelerate, and I need to overcome viscous. And what is my driving force? Is pressure. Okay, so that means that the pressure will now start dropping more rapidly. So that's the answer. So okay, most of you could guess it without. So you can see that that's the advantage of going in the fully developed region. So once we understand the fully developed region, okay, we can look at this developing region without too much of a difficulty. At least we know we are not giving you exact expression for this, but we know right away that this is how the pressure should vary. Right? So and that means that if I assume everything is fully developed, okay, now if I want to use it practically, then if I want to use it practically, I will say that I will, let us say 90% of my pipe length or my channel length is fully developed, 10% I don't know. So I will still do my calculation assuming 100% is correct, okay, and then I will put it some sort of, I know that in the 10% there is slightly more, I can put a small correction factor to that and I can be done with that. So this is just one approach. I'm not saying this is the best approach, okay, but this is one approach. You can say that, okay, I can assume everything is, and then then people will start saying, okay, this is like entry losses, this loss, that loss. So you start putting in K factor, if you recall, in your pipe losses, okay. So and you will get something similar. I mean, then you can put all those as entry loss, exit loss, and take care of all these that way. Okay. Now, because we have rewritten this equation, let us also remind us that, okay, if this was not a channel flow, if it was some other cross section like a pipe, then what would happen? Yeah, so same argument, whatever we have said till now, same argument will apply, and you should still get back to the same equation, which is this equation here. Okay, because in the fully developed region, okay, there is no acceleration. Okay, if there is no acceleration, the pressure force, these are the two forces, and they have to balance each other. So you can see that this result is quite profound in itself. Okay, it is telling us that irrespective of the cross section, I can take a circular cross section and I can take an arbitrary cross section. Okay, I can take this cross section and I have flow across in this sort of a cross section. This is my cross section through which the flow is happening. As far as this cross section is not changing, so it's the same cross section that I'm having throughout. Okay, I should still be able to satisfy after some developing condition. I should be still able to satisfy this condition here. which means the pressure will always drop linearly. Of course, velocity may not be very easy to integrate. Okay, I mean, there maybe I will get a second derivative also. I mean, you will get, essentially you will get an equation like this, because here we are considering the effect of two walls up and down. If you have side walls also, they will also have a boundary layer developing, and that will also start influencing the result. So the result, the equation that you will get is not just this term, but you will also get this term here. And you can see that this equation is now going to be applicable to even a geometry like this. Okay, and this is all we are just sort of deducing from this one equation here. So you can see that that's the power of looking at this channel flow. And so thanks for this question. It is actually brings out all these additional aspects that I mean I had not elaborated upon. Okay, other questions? Okay, so we will close this topic then. Channel flow we have done, and as we said that you can find out the flow rate, etc., related to pressure drop and all. So there are quite a few expressions which are given in the book, okay, which I'm not driving, but I mean you have everything to drive those expressions if you want. Okay, again, any questions before we go to the next problem? So if you remember, I mean, if you have seen the homework, I think I have posted the homework, right? So where I said, okay, please find out, okay, maybe I have not. Okay, so there we would like you to work out the solution for a pipe flow. Okay, same thing, pipe is so important, and channel flow, I mean, there you will have to work with the cylindrical coordinates. Here we are not working with cylindrical coordinates, it's much easier. So we take the easy problems, as somebody pointed out. We take the easy problems here and leave the difficult problems for you to figure out. Okay, so it's not that way, but I mean, the idea is that we have covered all that aspects. We are just asking you to go back, and if you have understood it, you can apply in a different scenario as well. Okay, so the next problem that we will take is a suddenly started plate. So we will have to understand what we are trying to say. This is also known as the Stokes' first problem. So let us say that we have a flat plate. So this is a plate. This is my fluid region. So at t is equal to 0 or t less than 0, so plate is stationary. So there is nothing happening. Okay, everything is stationary. Okay, and at t greater than equal to 0, we start moving it with a uniform velocity. Plate moves with a uniform velocity. Capital U. Okay, so is the situation clear? So we are again keeping a very long plate, again very long in the x direction, very long in the z direction. So this is a very long plate that we have. Okay, and suddenly I start moving it. So it was before that it was stationary, and we are only interested in looking at one side of it. Okay, so we can look at both the sides, but here we are just saying that we will confine our attention to one side of it. Okay, now here what do we expect to get? First, what sort of a flow should I expect to get? So you can see what will happen to the fluid now. Fluid was initially static. Okay, now it will start to move. Okay, by the way, last time somebody asked about this pressure. Okay, and we said that we want to answer that. Pressure variation in the lateral direction. The same thing is here. See, normally there is a hydrostatic pressure, which normally we don't bother about. Okay, because we know that we can account for that if that is important. So that's a simple answer to the question that has been given. Okay, so you can take out pressure, and other way to think about it is that I can take pressure and I can absorb this rho gh in that pressure itself. Okay, there are simple ways to do that as well. Some mathematical transformations that you can do for that. Okay, so that's why the pressure rho gh will not show up in most of the time. Yes. No, but the point is that whatever is the pressure here, okay, the pressure here, if this is a gravitational field, whatever the pressure here and between this point and this point, what you are saying, if it is open, then the top pressure at the top is atmospheric. Here we are saying that whatever is the pressure here, it should be pressure plus rho gh. Yeah, so that's one way to look at it. Other way to say that, okay, rho gh is there, but gets absorbed in pressure. So there are a lot of ways, but the bottom line is that we don't bother about rho gh. Okay, it can be taken care of in a very simple way, and therefore rho gh is never bothered. We don't bother about it. Okay, and that's why we never show the direction of gravity in any of these, because we are not bothered about gravity. So whether the channel is oriented horizontally, vertically, at some angle, etc., we are not bothered about that. Okay, so here, what do you expect to see? Initially, the fluid is all static. Now, when the plate starts to move, then the first layer which is there of fluid will start moving with that, with this. So, if I look at this depth, so the fluid which is here will start moving. So, whatever is, so this is a small region in which the velocity will start moving. And then what would happen? More of this region will start feeling that there is a motion. So, you can show that something like this will happen. This point is anchored because this is always going to move with the velocity u, capital U. Okay, so this is, and therefore the fluid next to the wall is also moving at capital U. Okay, but the fluid which was earlier only up to this point was seeing that there is a motion. Now at a longer time, so this is at time t1, and this is a situation at time t2, where t2 is greater than t1. And if I look at t3, then of course I would expect to see that a longer distance, the information has traveled to a longer distance, correct? So that's the situation that you are getting. And you can see that this is like how the diffusion is going to happen. So it is just telling us that plate starts moving, and then there is a diffusion process which is telling us that, yes, please start moving now, okay? Or it is getting dragged, the subsequent layers of fluid are getting dragged because there is a motion here which has been set up. Okay, is this clear? Physical situation clear first? Okay, now what is very clear is that with this solution is going to depend on time, right? Now, what are the other things? Again, we will use the same sort of a coordinate system, x and y. X is, let us say, along the direction of the plate. Y is, it is perpendicular to the direction of the plate, and z is the third direction. And we have already said that the plate is very long. So plate is very long along x and y directions, x and z direction, sorry, x and z directions. Okay, so here there is no fully developed, right? But what is here? Same situation is going to be applicable for every x, correct? Because the plate has been very long. So if I see here, if I see here, will I see any difference? No. So I will say that dou u dou x is equal to 0 because plate is very long. Because plate very long in the x direction. Anyway, there is no variation along the z direction. It's the same thing, no change would happen along the z directions. And z direction, there is no action. You can show that everything is 0 in the z direction. So we are not going to bring that equation in. We are only going to confine ourselves to xy plane. And we will have things very similar, some things very similar, and some things very different. So again, start off with, we have already given you the sort of the process that one should follow. one should start from the continuity equation, right? The continuity equation will tell us that dou u dou x plus dou v dou y is equal to 0, which again gives us that v is equal to 0. I mean, dou v dou y is equal to 0. And again, v is also not a function of x. Okay, same argument is very long. And so that means that it can become, v can be a function of t, we don't know that. But you can see that v is going to be a constant otherwise. Okay, so v is a constant, and of course that constant has a value of 0 at the plate, and of course there is no time dependence of v at the plate. Okay, so that takes out any time dependence of v on time, for example. So there is no reason why should v start becoming a function of t. Okay, so that means that v is equal to 0 throughout. So the same argument that we had used. Okay, and similarly from the y momentum equation, we should be able to show that dp dy is equal to 0 as before from the y momentum equation. Now when we come to the x momentum equation, and of course this is where the action is, x momentum equation. So here you will get dou u dou t plus u times dou u dou x, v times dou u dou y is equal to minus dou p dou x. The rho here is equal to mu times dou to u by dou x2 plus dou to u dou y2. So same equation that we have just seen, and we can see that this term is 0, v is equal to 0, okay, and this term is 0. Now it comes to dou p dou x, we can say that the same pressure, let us say, is applied at x is equal to plus infinity and minus infinity. So we will consider the situation where we will consider that P at x is equal to minus infinity is equal to pressure at x is equal to plus infinity. Okay, so that means that there is no dou P dou x. Okay, so this is something that we are assuming, or we are sort of we are limiting ourselves to this case where pressure is not a function of x. So I can take out this pressure as well, and I'm left with rho times dou u dou t is equal to mu times dou to u dou y2. Okay, and sometimes we define it as a nu we define it as mu by rho, which is the kinematic viscosity. So I get dou u dou t is equal to nu times dou to u dou y2. Okay, so this is our governing equation. So you can see that this governing equation is very different from the governing equation that we had earlier, right? Now, okay, before moving ahead, let us just pause. Let me pause and see if there are any questions here, whatever we have done. Yes. So we will consider. If you want, you can say assume. I don't have to. I just say consider. We are only considering the situation. We are not assuming anything. We are considering the situation. So I want to use the word consider rather than use the word assume. Assume means that we have to arbitrarily remove certain things, and therefore we have to assume certain things. Here we are not assuming anything. Simply considering that this is the case. Any other question? So otherwise the simplification is quite straightforward. Okay. So if you have to just recall, the continuity equation is still the same. It still gives me v is equal to 0, because of which y momentum equation still gives me dou p dou y. Okay, And when it comes to the x momentum equation, these two terms, not all the terms or not all the acceleration terms or the inertia terms are 0. Okay, these two terms are 0. The viscous term, one of the viscous term is 0 as before, but one unsteady term as well as the viscous term and the pressure terms would remain. So we said that we are not going to consider the case where dp dx is not equal to 0. Okay, that makes it too difficult for us to solve. So we get rid of this by assuming that this is what applies, and therefore this is the equation that we get. So yes, flow is moving because of dragging of the plate. Yes. So whatever is the force, shear, viscous forces that gets applied on the plate because of the dragging, that has to be supplied. Okay, and it has to be exactly equal so that there is no acceleration, net acceleration of the plate. That's what it means. And if this force varies as a function of time, then you have to keep on adjusting your forces that you are applying such that the plate continues to move with a constant velocity. That's the assumption that you have. That's not an assumption, but that's how you're setting up the problem. Okay. So what type of an equation is this? This is a, sorry, I did not understand hear any single thing. You have to be louder, please. Is steady, unsteady and linear. Okay, and it is a PDE, partial differential equation. It's no longer an ODE, right? So ODEs are easier to solve. Of course, not all ODEs can be solved, but these are easier to solve. And ODEs are easier to solve, and here we are looking at a PDA, which is even more difficult, right? And to solve that, we will see how to solve it. But to solve that, what are the conditions that you need? We need to still supply some boundary conditions and initial conditions. So what are the initial condition? So I want you to write the initial condition. U at time t is equal to 0, and let us say at all y's, what was the situation? Velocity was 0, right? So this is my initial condition, that at time t is equal to 0, at all y's, u was equal to 0. Now what are the boundary conditions? U at, so what, at the plate, okay, at the plate, which is, so time t greater than equal to 0, at y is equal to 0, we have velocity u is equal to capital U, right? So this is one condition that we get. How many conditions do we need? We need two conditions. You can see from here, I need to be able to integrate. I will be integrating y twice. So I need to have two conditions for y. So what is the other condition? So y tends to infinity. So infinity condition. So here you can use the infinity condition. Sorry, you were saying something. Same thing you're saying. Okay. So at y tends to infinity. So the other boundary condition is, boundary condition 2 is that u at t greater than equal to 0, y tending to infinity, my velocity is still 0. Okay, so I'm assuming that, I'm not really assuming in some sense, I'm not looking at till infinite, after infinite time, of course, maybe infinite distance away, the flow will start moving, but I'm not looking that far. So that's a sort of a statement that we are making. Okay, so that in the time period that we are looking at, the flow at very far away is still stationary. So now the question, so we have everything. So this is my now, this is, I mean, in some sense, I have done my my physics is done. My problem is now a mathematical problem. This is my governing equation. These are my boundary conditions. Solve it and get the answer, right? So that's why I pause here and see if there are any questions with the physics. Okay, now it's a matter of trying to solve this. So how do we solve this? So we will use, so there are several techniques, several ways to solve this equation. We will use one method, which is going to be far more far more physical in nature. So we will assume, we will just make a statement that if I look at velocity at any point, at any time, so we have removed the figure here, but this is my plate, this is my point which is of interest, let us say. So what will the velocity at this point depend on? So this is a function of, so how fast this flow is moving, this plate is moving, correct? This is a function of capital U. It's a distance, it's a function of what is the distance I'm looking at, right? So it's a function of U, sorry, Y. It's a function of time, right? So initially, for example, there is no velocity here, but after some time, the flow will start moving here, and the velocity of that will also start changing. So it's a function of time, and it is a function of how fast the information is going to diffuse. Okay, so which is a function of essentially my new parameter here, new here. Okay, so we are trying to do essentially dimensional analysis and say that, okay, this is what all things will depend on. Okay. Now, if I look at, so is this clear first? How did we make this set? And again, in this problem, it is much easier to see how we have to form this set. Okay, because everything that we can consider, it would depend on is already here. It depends on the distance, it depends on the time, it depends on how fast the plate is moving, and it depends on how fast the information is diffusing to this point, which is my parameter, which is measured by the parameter nu. So it's a function of all these four things here. So if I use non-dimensional, if I say U by capital U is a function of YT nu, okay. And we are going to say that now what group can be formed from here? So this is having how many dimensions? Y is being measured in meters, this is being measured in time, it is measured in seconds, this is measured in meter square per second, okay. So you can see that there are only two dimensions involved, and there are three parameters here. So I should form 3 minus 2 or one group. And what is that one group? You can see that it is, if I multiply these two, it will become y upon square root of nu t. If I look at nu into t, then my dependence on s goes away and I get only meter square. Okay, and then if I take a square root of that, that becomes meter, which I can divide it with this meter, and you can see that this is now becoming a non-dimensional group. Okay, so essentially we are using our dimensional analysis and forming this group here. Okay, any questions here? So now once we understand this, we are going to introduce, for mathematical simplicity, a factor 2 here. Okay, this is only for mathematical convenience that we put a factor 2. This is non-dimensional, half of that is also non-dimensional. So there is that way, there is no issues. So instead of considering it as a function of this, we can consider it as a function of y upon 2 nu t. Okay, so you can see that my equation now is u is equal to capital U times f of eta. This is the equation that we now have. So what is the next step? Okay, again, I'm asking, pausing here and saying, is there any questions here? Is there any issues? So what is it telling us physically? What is this parameter? If I have to pause and ask us, what is this parameter? What does it physically means? So it means that although y and t are two independent parameters, in this problem, only what is important is y upon square root of t. Okay, so y upon square root of t, and nu is anyway a constant, so I'm not thinking of spelling out nu again explicitly here, but y upon square root of t, if is that same, then I will start seeing the same thing. That's essentially what it means. So if my y is more, then my t should be more. Okay, so then I get the same value of y by square root of t, such that if I see the same value of y by square root of t, then I will get the same behavior. That's essentially physically what it means. And how are we deducing that? We are not just claiming anything. Why did I put a square root in time? Now, not a third power, 1/3 power, 1/4 power, or whatever other power. We are getting it from dimensional analysis. And we know that this is because it is like, it has this units, and therefore this is a non-dimensional group, and therefore it is going to be a function which is dependent on y upon square root of t and not any other power of t, not like y upon t or y to the power, y divided by t to the power of 1/3. Understood? So the next step is to transform this equation. So what I want to do is to find out what is my dou u dou t. So what is my dou u dou t? So I have to take a differential of this with respect to time. So u is anyway not is a constant, it is not changing. So then I get df dt, okay, which I can say is u times df, or maybe a partial should be used here, df d eta and dou eta dou t. Okay, I'm not going to do everything because you have all the expressions. Eta as a function of t, you have, substitute that here. Similarly, if you get dou u dou y, it is going to be again founded in a similar manner, df d eta dou eta dou y. Okay, and from here find out what is my dou 2u dou y2. Okay, so these are small exercises I'm leaving behind for you. Okay, we have all the expressions, find it out. So what we will see now, okay, but before again I switch the boards, any questions here? So what we will see is that this equation now will transform into an equation which is d2f d eta 2 is equal to 2 minus 2 eta df d eta. So this is what this equation will transform to. Okay, so you have all these things, just substitute it back into this equation here, into this equation, and this is what you would get. Okay, by the way, I have again made a small typo here. We have been using capital F here, so let us use capital F here. Or we can use a capital F here and make minimum changes and keep this as a small f. Then we can use a small f here and a small f here. Okay. So we are consistent now. And now what type of an equation is this? Linear ODE, right? So the good thing is now that the PDE, so why did we do all this? You can see whatever we are doing here on this side, we have done it and that has allowed us to convert a PDE to an ODE, right? So now we have gotten a ordinary differential equation. Okay. Now what about the boundary conditions, initial conditions? How many conditions do we need here now? 2. Here we had how many? 3. Okay. So in channel flow, we said there are 3 conditions and we need only 2. You could just arbitrarily pick any one, and we showed that the third one will automatically get satisfied. Will it happen here? Yes, no. The answer is no. Okay, so we have to be careful about what we are doing. So that's where we will see that there are certain ideas which are actually buried in here. So if I look at, so what are the conditions now? So we were applying this y boundary conditions at y is equal to 0 and y is equal to infinity and t is equal to 0. So now if I look at eta is equal to y upon 2 times the square root of nu t. Okay, so when y is equal to 0, so let us just look at this first condition. So initial condition is now becoming, is giving us that u at, so this is being applied at t is equal to 0. So at t is equal to 0, what is the value of eta that I am getting? Is infinity, right? So I get eta tends to infinity or is equal to infinity, whatever it tends to infinity. I get that my u is equal to capital U, and when u is equal to capital U, what is the value of f? It is 1. Okay, so I'm using this equation. I'm using this boundary condition, initial condition. In this initial condition, I'm saying that at t is equal to 0. So at t is equal to 0, here eta is infinity. Now, for then, if eta, and then what should I get? I should get, sorry, u should becomes equal to 0. So if u is equal to becoming 0, then u was this expression here, u was this expression here. So u is becoming 0, that means that f should now become 0 because capital U is not equal to 0. So then this should be 0. Now what about the boundary condition 1? So boundary condition 1 is telling me that at y is equal to 0, u is becoming is equal to becoming capital U. So what does it mean? Now you tell me. At y is equal to 0, what is the value of eta? Eta is 0. So eta is equal to 0. And what about u? Sorry, what about f? F is now becoming 1. Right? Everybody with me? Or rather, anybody not with me? How we are doing this? So I've showed you how to transform this equation. Here we are just showing how to transform the boundary conditions. Any questions here? Now apply boundary condition 2. Y tending to infinity, eta is infinity. So y eta is becoming infinity. Now what is happening now? U is becoming 0. Okay, u is becoming 0 means what about f? U is 0, f is becoming 0. So f is 0. So you just saved. You have been saved. Why? Because these two conditions are exactly the same now. So although you said that you have 3 conditions, okay, when you go to the transform thing, you are only having 2 conditions. Okay, which is what you needed. If you had a third condition also present, then there could have been a contradiction. Okay, and this is actually not speaking, this is a very, very subtle idea, and this goes back to the fact whether you can do all this or not. Okay, so this is when it sort of says that whether the similarity solution would exist or not. Okay, so if it is existing, then you will see that this sort of a transformation, more number of boundary conditions would map automatically to just the right number of boundary conditions that you need. Okay, so is this point clear? So now, really speaking, it's a very straightforward integration that you can do. So we can assume that, or we can take an introduce an So now we have this problem statement. Okay, earlier we had this problem statement. We had a much harder looking problem, OD. We had a PDE, but now we have a much simpler looking equation, which is an ODE now, and this is much easier to solve. So let us introduce an intermittent variable, let us say f prime, which is df d eta, and we can directly integrate it with that. So we get df prime d eta is equal to minus 2 eta f prime. Okay, so I integrate this, you get f prime is equal to a times exponential of minus eta square, right? That's what you would get from here. And then we integrate it again. So I get df d eta is equal to this. So I integrate it again. I get f is equal to a times exponential minus eta square d eta integral plus another constant of integration. Okay. So I know that eta is going from 0 to infinity. Okay, so I can take this from, let us say, 0 to eta, and now what is the value of c that I will get? So value of c I can get from here. So at eta is equal to 0. So at eta is equal to 0, if I put eta is equal to 0 here, this integral is 0. This is 0, f is equal to 0. I'm essentially applying this condition here, eta is equal to 0, and I should get f is equal, no, so yeah, so this condition, this is becoming 0, and this f is becoming 1. So that means that c is equal to 1, right? So this c is now 1 from boundary condition 1, let us say. So c, so boundary condition 1 tells us that c is equal to 1. Now I apply the other boundary condition, which is, say, let us say boundary condition 2. Now boundary condition 2 tells me that as this becomes, eta becomes infinity, so I'm looking at integral of this, and then my f should become 0. Okay, so that means that this entire integral of a times a, of course, can be pulled out, 0 to infinity of exponential of minus eta square d eta is equal to minus 1, right? Okay, by the way, what sort of a function is this now? How do I integrate this? This is non-integrable, so we defined another function. The error function becomes like an error function. Okay, so we can substitute this is like an error function which is there with us. Yes. Yeah. Yeah, so this is right now written with the, here you can introduce a dummy variable if you want, but this is a function of eta now because this is all there is to it, right? And so this is where the dependence on eta is. So this is still a function of eta. And we are now saying that if I take infinity, eta is equal to infinity, then of course this error function will take a particular value, okay, with some square root of pi by 2. Okay, so that is what I would get here. So this answer turns out to be not so trivial. So f will turn out as 1 minus error function of eta. Okay, everybody with me? What is happening here? Right. So if you have to just very quickly go back to where, I mean, how we solve this problem. So we had dou u dou t is equal to nu times rho to u dou y2. This was the equation that we had to solve. And we said that we will solve this using the similarity route. Okay, so we will argue this is our physical arguments, and this from this physical argument we form two non-dimensional groups, u by u and this other non-dimensional group, and there has to be some functional relationship between these two. Okay, and from here, so once we determine that, so this is what we are looking at. So this is now the similarity variable. Eta is some sort of a similarity variable, and this similarity variable is what is connecting. Yes. Yeah. So there are three independent variables and two dimensions. So 3 minus 2. So only one, that is what you would form. Non-dimensional group is what you would form, and which is what this is. Okay, so this is what u is now. Okay, and now what we do is once we recognize that this is the form in which we can look for the similarity solution, then we look at transform this equation into this, I mean, into the new equation. Okay, using this idea, I mean, or using this chain rule or differentiation like what we have done here, just because of simplicity. I mean, we don't want to get into the algebra here, so we have not given you the expressions. You can work it out. But once you have all these expressions, you put it into the equation, and this is the equation that you get, right? And once you have this equation, you transform also the boundary conditions and the initial conditions, and you get these are the new conditions which are coming out. So these are the conditions that you are now getting. Now, once you get that, okay, so and we first make sure that everything is consistent, and we said that it is consistent because these two conditions which are applied at different space and different time, okay, but they are turning out to be consistent, and because of which we can actually proceed with the type of arguments that we are making here. Okay, and then we say that, okay, because that is happening, now we just come back to our equation, integrate it. We have integrated it twice. First, we introduce this f prime, which is df d eta. Okay, so this becomes df prime d eta, this first term here, and my second term is minus this term here. Integrated once. This is a straightforward integration. Okay, I can take eta prime, for example, so I can write it out as df prime by f prime is equal to minus 2 eta d eta. Okay, so this will give me a log term, this will give me eta square term, and then log term I can convert it, take an exponential of both the sides. So this is what I would get here. Okay, and then a constant of integration will get generated, which is nothing but my a. Okay, so that is how I write this term, and then I integrate this equation again. Okay, so if I integrate it again, this is what I get. Now I use the boundary conditions. The boundary condition 1 gives me that eta is equal to 0, I get f is equal to 1. So when eta is equal to 0, this whole integral is becoming 0, then c is becoming 1. And the boundary condition 2 gives me that when eta is becoming infinity, this f is becoming 0. So then this c term will still remain, and that's what we get here from here, minus 1. Okay, and then if I put everything together, I will get that f is nothing but 1 minus exponential of eta. So this, so sorry, not exponential, 1 minus error function of eta. Error function is, this is nothing but my error function, so I will get an error function here. Okay, so this is the solution that we are getting. Okay, so we have only a few minutes, so we can spend either little bit more time on this, or we can just pause here. I mean, so in some sense we have solved the problem, it's already done, and we can now look at a few features from here as to how thick this layer is going to be. For example, we can look at that. So if I look at, so I will have essentially profiles like these coming out. Profiles like these is what I would get at different times. So this is at T1, T2, and T3. Okay, this is moving at, this is my velocity u. This is how the velocity is varying. Now we have the exact expression. This is how things are varying. Now from here, from this eta and f, you can go back to your physical parameters. Okay, f was nothing but u by u, u by capital U, and eta was nothing but y upon 2 times the square root of nu t. Okay, so essentially you get u by capital U is equal to 1 minus error function of y upon 2 times the square root of nu t. So this is the solution that we have now with all boundary conditions, everything already applied in there. Okay, so this is what we are plotting at different times. This is what you would get. And it is telling us that if I, any distance and any time I take and I form this group, then I will have only one curve, okay, which will be, let us say, this curve. Okay, so all these different times will collapse into a single curve, which is given by this curve here. That's essentially what it is meaning, and that's essentially what this is, what this theta is. So essentially it is saying that instead of looking at u as a function of y and t, here we are looking at f as a function of eta. F as a function of eta. Okay. And there is only one curve which is giving me this relationship, which is of course the 1 minus error function here. Okay. And from here, if we want to say that how far this information goes, so just like in boundary layer, I mean, this function will only go to 0 at infinity. So we can just say that, okay, if it takes a value of some value, let us say 5%, like there we had in boundary layer, it takes 95% of the velocity, free stream velocity. Here, let us say if I take the value as 5%, okay, from the same argument, we can see that this is the position. I can draw a line here, a parallel line. So this is, let us say, u naught. So this is, let us say, f is equal to 1 in the normalized thing. Then I'm looking at 0.05. I'm drawing a vertical line, and here I'm seeing where does it intersect. Okay, so I will find that it intersects at eta is equal to 1.38. Okay, so then the boundary layer, this thickness can be written as 2.76 times. So essentially it becomes, okay, so again, these are all simple. I think I don't want to spend time on doing this algebra, but what I'm saying is that if I look at a curve like this, and we can say that, okay, if I want to define a thickness, if I want to define some sort of a length scale, instead of trying to go to infinity, I will cut it out at some point. I don't want this function to go to 0. I will let this function go to only like 5% of the maximum value. Okay, so then I draw a vertical line, see where it intersects, and then based on that, I can define what is the thickness that I am having. Okay, so that means how far the diffusion phenomena is happening. Okay, and that will turn out to be 2.76. So that the delta will turn out to be 2.76 times. So again, it is coming from here. It is taking this is coming from this value, square root of nu t. Okay, so where y is this particular, so y is taking the value of where the function is 0.05. Okay, so that's the point that we are looking at. That's a corresponding point. So this is turning out at this particular position, which we are calling it as delta. And then this delta is 2.76 times the square root of nu t. So it says that as time increases, my thickness increases. So it's like diffusion is happening. So it's happening at the rate of square root of t, and more layers of the fluid is now feeling the presence of the movement of the plate at the top. Okay, so this whole problem is very interesting because it shows this diffusive nature. It shows that the diffusion essentially progresses at square root of t. Okay, so this is why this problem is so important or so interesting, is because it shows very clearly that this diffusion has this square root of t time dependence. Okay, so this is where we will stop. And okay, now we can talk about the mid-sem. The first thing is everything that we have talked about in the mid-sem, everything that we have talked about till now is included in the mid-sem. So that's the first point. Second point, people wanted to know whether there is we are allowing open book, open notes, etc., etc. So we are fine with that. If you want to bring in one sheet of paper with the formulas written down, any formulas that you want to be written down, anything that you want to be written down, let us say. Okay, you can bring that, and you can write the entire notes, the entire book. It's up to you, but one A4 sheet is what we have. Or you can write on both the sides. Let us also specify that you write on both the sides in your own handwriting. The only issue is that only constraint is that it has to be in your own handwriting. You are not expected to photocopy a book or anything, but if you write it in your own handwriting, it's fine with me. Okay, so anything else, anything about the midsem that we need to clarify? Yes. Examination. Please check the timetable. Okay, I did not realize it's already 11:01, so we'll have to stop here. And all the best for your exam now.